Hello and welcome back. Let's talk about derivatives of logarithmic and exponential functions. All right. So the derivative of the natural logarithm, the natural log of x, remember that's an L, logarithm. It's not an I. It's not n. It's not a thing in math. ln is an L, not an I. The derivative of the natural log of x is 1 over x. That's it. If it's not a natural logarithm and it's any other logarithm that we write with a base b, the derivative of log base b of x is 1 over x times the natural log of b. So really it's the same. It's 1 over x, but we have to adjust to put the base in our natural log format. All right, so that's the only part. It's just this constant that is an adjustment that takes the logarithm from the base and it naturalizes it. In general, the chain rule for logarithms, whether it's the general log base b of x or the specific natural logarithm, the derivative of the natural log of u is u prime over u, also known as 1 over u, times du dx, derivative of the outside. So derivative of the natural log is 1 over u, times the derivative of the inside, du dx. But I like to think of it as the derivative of the inside divided by the inside. That's it. And if you have a not in log base b, you have to adjust it with the ln of b in the denominator. That's it. All right. Derivative of the inside divided by the inside. That's how logarithms roll. So let's find some derivatives. If f of x equals the natural log of x plus 3, inside of the natural logarithm is x plus 3. The derivative of x plus 3 is 1, right? Derivative of x is 1, derivative of 3 is 0, 1 plus 1 is 0. Derivative of the inside is 1, divided by the inside itself, x plus 3. Boom, done. Derivative is 1 over x plus 3. Log base 3 of x. Because there's nothing going on with the x itself here, I know that I'm going to have a 1 over x. Because this has a specific base that is not a natural log, I also know that with that x in the denominator, I'm going to have to adjust with the natural log of 3. That's it. If f of x is log base 173 of x, I know that the derivative is, because this x is by itself, it's 1 over x. Because this is not a natural log, I know it has to be the natural log of 173. In this case, my base was 3. It's the natural log of 3. Don't let it be more complicated than that. If the base is, if we're already a natural log, we're good to go here. If it's not a natural log, we take care of it. Natural log, f of x is the natural log of 3x squared minus 7x. So the inside is 3x squared minus 7x. The derivative is 6x minus 7. So the derivative of the natural log of 3x squared minus 7x is derivative of the inside, 6x minus 7, divided by the original inside, 3x squared minus 6x. You can't cancel the 6 and the 3. You can't cancel 7s. You can't cancel minus signs. There's not a 3 in everything. You can't cancel it from anything. There's not a 7 in everything, right? And everything is separated by plus or minus and across the fraction bar. So if there's a plus or minus, x, 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 oh, this one has no x, so it ruins it. All right, we can't simplify it at all. All right, number 4, g of x equals log base 5 of 17x minus 12. Inside of the logarithm is 17x minus 12, and the derivative of 17x minus 12 is 17. So the derivative of log base 5 of something is derivative of the inside divided by the inside multiplied by the natural log of the base 5. Right? The inside is 17x minus 12, so I put that in parentheses. Don't make it harder than it actually is. All right. Moving on, more examples. Here we go. g of x equals the natural log of x over 2x minus 1. Now, I said over, right? So there's a quotient kind of built in. I notice my inside is x over 2x minus 1. To find the derivative of the inside, I have to use the quotient rule. Quotient rule says low, d high. And if you need to, write it over here. I'm not going to use the same color. Default is blue. I need to switch that. My low is 2x minus 1. My high is x. I can find d low is 2, and I can find my d high is 1. So if I need to, I can break this down using the quotient rule. Low, d high, minus high, d low, all over low squared. Distribute. Multiplying by 1 is pretty easy. That's just 2x minus 1. Minus 2x. 2x's cancel out. I'll end up with negative 1 over 2x minus 1 all squared. But remember, we're not just looking for the derivative of the inside. We're looking for the derivative of the natural log of x over 2x minus 1. So I have here the derivative of the inside. And I have here the inside itself. Right? That's all the derivative of a natural log is. The derivative of the inside divided by the original inside. But instead of dividing by this fraction, because honestly, two fractions inside of a bigger fraction, please. Instead of dividing by this fraction, we can multiply by its reciprocal. Now we'll have negative 1 over 2x minus 1 squared times, now we flip this one, 2x minus 1 over x. Notice this 2x minus 1 cancels one of them, so instead of 2, now I have 1 remaining in my denominator. And I can simplify this as multiplying across to get negative 1, multiplying across to get x times 2x minus 1. And if you wanted to, you could absolutely call that 2x squared minus x, and that's cool. All right, but this is the answer that I would be entering in my answer sheet or on your homework, online homework system. The natural log of the absolute value of 2x minus 4. All right. The inside is an absolute value. Uh-oh. Here we go. But we know the derivative of an absolute value, right? It turns out that the derivative of an absolute value, here's what I want to do. My out is just absolute value, and my inside is 2x minus 4. Derivative of the outside is the absolute value of whatever over itself times the derivative of the inside. All right, so derivative of the outside has this format. It's the absolute value over the function without absolute values. Leave the inside alone. That's how I get the 2x minus 4 is inside here. And then multiply by the derivative of the derivative of the inside. Derivative of 2x minus 4 is 2. This 2 is being multiplied in the numerator. It's always in the numerator unless specified otherwise. When you're just multiplying, remember 2 is the same as 2 over 1 if you need to. So as I simplify here, I see that this 2 times the absolute value, whatever, 2x minus 4, they have a 2 in common. So I can cancel this 2 with the 2 I factor out. But that's only the inside. The inside had some stuff going on. It was some crazy stuff going on. Here I used a quotient rule. Here I used the absolute value rule. But overall, the derivative of the natural log is the derivative of inside, which we found right here, derivative of the inside divided by the inside itself. Instead of dividing by 2x minus 4, I multiply by its reciprocal. Same idea here. Divide by a fraction is multiplying by the reciprocal. Absolute values cancel out. I end up with 1 over x minus 2. It turns out absolute values are pretty interesting inside of logarithms. All right? You have to do some work sometimes. All right. What about exponential functions? The natural exponential function, and this is why it's called the natural exponential function, this is the greatest, of all functions, the derivative of e to the x is itself. That's it. The derivative of any other base to the power of x, we again adjust by that natural log of b. That's it, right? If it's an exponential, if it's e to the x, the derivative is itself. Cool. If it's any other base, we have to adjust using the natural log in order to adjust the base to the natural exponential base. The chain rule with exponentials, if we're taking the derivative with respect to x of e to the something, our derivative is e to that something times the derivative of the exponent. So I think of it as a derivative of exponent times multiplied by, times has fewer letters, times the original function. Let me show you what I mean. E to the x squared. My exponent on e is x squared. The derivative on x squared is 2x. The derivative of e to the something is the derivative of the exponent times the original piece itself. U prime, right? The exponent is our u. U prime times e to the u. Over and over again. The only time I have to worry about it is when the base of the exponential is a different number, not e. So let's look at number 2. F of x equals e to the 1 minus x. My exponent is 1 minus x. My derivative of the exponent is negative 1. So the derivative of f of x equals e to the 1 minus x is u prime times e to the u. Derivative of the exponent multiplied by the original. E to the 3x times 4x minus 7. Now my exponent, 3x times 4x minus 7, and I could distribute that and just take the derivative, or I could use a product rule, derivative of the first, leave the second alone, plus first times derivative of the second, distribute and combine. But when it comes right down to it, my derivative, here's my original, it's always going to be a copy, derivative of the exponent multiplied by the original. And I use the parentheses because you always need to be good with your parentheses, so you could show all of that exponent derivative is multiplied by the e. What if it's not e? No biggie. All right, we only adjust it a little bit. My exponent, my u value, is x squared minus x. The derivative of x squared minus x is 2x minus 1. Pause to remind yourself if you need to. When I put this together, I will have the derivative of the exponent times the original as it was given to us, and then adjusted, whoops, that's not an h, adjusted for the base. All right, the base, the 3, base of 3. Here we have 7 to the power of, oh, my dogs are barking again, yay. 7 to the power of the absolute value of 2x plus 5. My exponent is the absolute value of 2x plus 5. The derivative of an absolute value is always the absolute value of the inside over the inside itself. All right, absolute value. So times the derivative of the inside. If you want to add that to your formula sheet that you started in section 11.1, that's a chain rule with absolute values. And I think it's the first time I've ever actually written down in formula form. So if our exponent is the absolute value of 2x plus 5, our derivative is the absolute value of 2x plus 5 over 2x plus 5 times 2. That's the derivative of the inside. And that's 2 times the absolute value over 2x plus 5. My 2's don't cancel because this 5 messes everything up. Right? The 5 doesn't have a 2 in it. Separated by a plus or minus, so it matters. So when I put this all together, though, I will have the derivative of the exponent times the original function itself, and then that's my Stella. One moment, please. And then we can multiply by the natural log of the base to finish it off. Like seriously, she couldn't be quiet for 10 more seconds. I love that little beastie. All right. Derivatives of logarithmic and exponential functions. Chapter 11, you're creating a formula sheet for yourself of all these different rules. And in chapter 12, we're going to use those rules to like learn some stuff. But we're learning about functions. We're learning about, these are just the tools. Right now we're learning to hammer a nail. Chapter 12, we're going to learn how to build a roof and like actually use that hammering for something that makes sense and is helpful. All right, that's it. Thanks for listening.